Hello and welcome back to AB1202 Statistics and Analysis Week 11 tutorial. Our topic today for discussion is non-linear regression. If you have not studied or viewed the videos for linear regression analysis, I will suggest you have a look so that we can build on top of that knowledge. And we start off with just having a quick review of the concept underlying nonlinear regression. Then we move on to talk about transforming functions. We will focus on just one, right? So this is the logarithm function applied to a random variable x. And then we want to um, use that transforming function to try to linearize nonlinear models. Okay, so linear models is a very special subset of nonlinear models. Nonlinear models, there are many, right? That can involve exponentials, logarithms, sine, cosine, and many forms. Basically, all kinds of models are nonlinear in general, and only when they are, the coefficients are specifically restricted to be constant, they are also linearly combined by addition, then we have a linear case. So linear models are very very niche, very specialized. But then we also encounter linear models a lot. That's why we started with that. And also, of course, the mathematical analysis is way easier, right? So we're going to talk about specifically two kinds of nonlinear models: the power index models, right, where y is some kind of constant times x to the power of b1, and the exponential model, where y is actually b0 times e to the power of a constant times x. So in one model, the x sits on the ground and raised to a constant power. For example, x squared, x cubed, or x 3.55, right? The exponential model is a lot more explosive, right? Where x sits on top, and as x gets larger and larger, e to the power of a larger and larger number basically explodes, right? So this will be another nonlinear model that is quite commonly encountered. Actually, both of them are, and that's why we want to look at that, right? So other models like sine, cosine, and all those, well, we'll reserve for some other discussions another day, right? Okay, so and then we want, after this, we want to also include a bit of discussion on the interpretation of coefficients, because in linear case, unit increase in x might lead to constant increase or decrease in y, and we can interpret that because it's linear. But in non-linear case, how do we interpret that constant coefficient of x, such as b1 here, right? So how do we make sense of it? So that's the interpretation. Okay, so let's begin by first understanding the concept. And I'm not going to write a lot of words here, just basically telling you a story, right? So how do we go about it? Of course, mathematically, we have to go through all the rigor of proving and doing the right thing, but it's good to know what are we doing, right? When we discuss about log x, and why do we discuss about that, right? So the idea is when it's nonlinear, we want to mold or transform the model or the random variable itself. They are different, right? So if we just change or massage the random variable, squeeze it or expand it, right, or do it non-uniformly, large values we squeeze more, small values we squeeze less, that kind of thing, that will be transforming the random variable. Or we transform the model. For example, we apply logarithm to both sides. So we already have a model, and we want to kind of like a loose word is called flattening it, right? So we want to like linearize it. Can we massage the whole model? Remember, my model is basically what some of you may be thinking of, the equation, right? But I really avoid using the word equation because we are not trying to equate both sides. We are actually more like using the right hand side to explain the left hand side, right? Statistically, based on many sets of data. So uh, so the second approach is what we'll be doing later on, to apply a transforming function such as logarithm on both sides, and then see if, right, we can get a linearized version. So the idea is, once we can flatten it to a linearized version, then it'll be back to our familiar territory. We just apply the linear regression concepts. Be careful with the interpretation of the coefficients, right? And um, we should be okay. What is nice is we don't need to reinvent, right, or invent a new theory, one for power index model, one for exponential model, and every time we come up with a new model like sine or cosine, then we have to rederive everything. That will be rather unproductive and makes things a lot harder to proceed, right? Yeah. So we try. Now, of course, the first approach, just applying a transforming function like logarithm to a selected variable, right? Oh, I select x to transform. Oh, I select y to transform, right? So you can do that by transforming the sample space, the scale of the axis, or by squeezing in or by stretching it out to make non-linearity linear or more linear than it originally was. All right. So some functions are really very disobedient, very naughty. That if you apply a simple transformation like logarithm, it's not sufficient to make it very linear. And then those are the wild animals, that wild models, wild random variables with wild distributions, very hard to tame. Then probably we have to do something else, right? So that's beyond our discussion here. Now, the way we discuss about nonlinear regression concept, right? One is by just applying a transformation function to a selected random variable. Now, select which one sometimes is a little bit of skill and art and justification. Does it make sense for me to do a logarithm? Is the range of the sample space for x for that random variable wide enough? Because if it's already narrow, then it's pretty much approximated by a linear uh, uh, kind of function anyway. So you may not want to transform it with logarithm, right? So we need to examine different aspects, right? Both the validity of the variable itself, the reasoning, is there a logic to do this transformation, and then also the numerics, right? The numbers in the data that you collected, are they bunched up together? If they are already bunched up together, you may not want to do this kind of nonlinear transformation to make it linear, but on a variable by variable basis. And the other approach is necessary, because instead of looking at a single random variable itself, one at a time, we are looking at the whole model, right, including the equal sign there, the model itself. So we need to apply uniformly both to the left and right. If we take logarithm of y, since our model declares that y is b0 x to the power b1, then we have to apply logarithm to right side. So that's the second approach. We'll see how we can do that in a while. Okay, so that's the brief idea of the concept. That means we change the nonlinear into linear, back to familiar territory, right? Then we apply linear regression. That's the approach we are going to take up. Now let's take a look at applying logarithm function to a single random variable x. First, I just clarified that logarithm function is the only function we are going to discuss. All right. So of course there can be more than just logarithm function as a transformation function. You can also use exponential. Like if it is not sufficiently uh, curved up because it's bending, it's non-linear in a way that it's bending too low, we can exponentiate it to make it pop up so that it appears more like a diagonal line, right? So that is back to linear. So if it's dented, we can exponentiate it. If it's popping up, right, too far out into the infinity zone, we can pull it back down through logarithm function. So we'll discuss this. Okay. So first of all, what is meant by um, applying a transformation function to a random variable x? So first, let's have a random variable. Yeah. So we have a random variable, and of course we have the probability, the PDF here, the PDF probability density function here, and I'm just going to sketch a quick one, which is more like a skewed, all right, non-normal random variable, where you see that large variables are very likely to appear. Yeah, so that these are large variables of values of x, and these are smaller values of x. So it is non-linear, and we would like, if possible, to make it more normal. As you can recall, many a times when we discuss about statistical concepts and tools, we assume, right, or we hope that the parent distribution x is already normal. But what if it is skewed, right? Non-normal in a sense that it is very skewed. Usually it's right skewed. Example might be, for example, the income of most countries, very rich people, right? Like having 10 million, 1 million, 10 million, 100 million as your salary, and that's pretty high. Those people exist, but usually not by a large proportion of the country. And then you have most people earning the middle class here, right? Somewhere in between. And then the low income families will be here. So hopefully not a lot as well, right? So typically most countries will be having this lump and then skewed very much to the right side. And we're not talking about we're not analyzing income for all countries right now, but I'm just saying that these right skew, more right skew than left skew, they occur rather frequently in population studies, in measurements, in business, in many contexts. Okay, so now what's going to happen? We would like, all right, the goal is to make it a little bit more normal, because it's not normal. And when you make assumptions like normal distribution, let's assume x is normal, we apply t statistic, and then there will be some discrepancies, and so there will be uh, errors or mistakes, and our conclusion, whether it's confidence interval or hypothesis testing, might not be reliable, right? So by transforming this into a more normal situation, we hope, right, that we will be able to perform those confidence intervals and hypothesis testing better. And the idea is that we want to apply a small force, because if this part looks normal, the left side, right, kind of looks normal. The left side kind of looks normal. We just want to squeeze in the right side. And the idea is that if the values are relatively benign, like pretty low on the x-axis, then we want to apply a smaller force. I just call it force first, right? So, and if it is a bit larger, we apply a bit larger force, but not so much as in overriding the first one. You still want to sort of stay in order. If you are larger than this value, then you, after transforming, you better be also larger than this value. So in the mathematical sense, it's called one-to-one transformation. It's reversible in that sense, right? So you don't change the order. And similarly, we want to keep doing that. And for very large values, you can see that we will not hesitate to apply a huge, right, the length of the arrow, trying to show the size of the force being applied. We will not hesitate to apply a huge force to pull it back, right? So the bigger your value of x as the x-axis, the larger the force will be applied in shrinking that value to a small number. So that after transforming, hopefully, right, we'll get a green curve like this. Like this part is going to be shifted somewhat, right? So it's not going to be totally immune to movements. And but then it will be shifted by just a little bit. And this part will be a lot. So the large values will be like pushed down to earthly values. So if you're 10 million, it becomes 10, or 100, something a lot easier to, or more comparable with the smaller values, right? So originally you have 10,000, 20,000, 50,000, right? Then you have people having 1 million, 10 million. So now the 10,000, 20,000 gets reduced to 3, 4, 5, and the 10 million, 1 million, 10 million gets reduced to 50, 60. Okay, it's more comparable, and it also becomes a lot less skewed because and more symmetrical, because logarithm is such a function where it doesn't like large value, right? It kind of reduces it down all the way to single digit, two digits number. So with that, then you can easily imagine that the original cyan curve here, the bluish color, gets reduced to or transformed to the greenish uh, distribution, right? And you can think of it as, once the value, for example, 100 gets applied to logarithm, let's just take base 10, that's easier, right? So if it is 100, it gets reduced to, all right, so let's say 100,000. 100 means 100,000. It gets reduced to 2. This becomes 2 because we apply logarithm. So if we apply logarithm, so log base 10 of x. Now, when I don't write the base, it is essentially referring to log, right? Base e, the 2.71828, and never-ending story number constant. So because in R, in Python, these are the spelling of the function, so I'm going to just stick to that, even though mathematicians will interpret log without any base as base 10, right? But I'm going to stress that it is actually base 10 by just writing base 10. And if it is not indicated, this could mean a general notion of logarithm. And mathematically, we'll prefer ln than log base 10 because it's just easier. E to the power of ln x is just x, right? That's a very nice inverse function there. And base 10 is easier for understanding because 100 is 10 to the power of 2, and base 10, right? 10 to the power of 2, we just take the index down, that's 2. So 100 gets reduced to 2, and so on and so forth. So you can see the power of this transform is really large, right? Large values really gets reduced to very decent, small, comparable values. Okay, just another quick illustration to home in on this notion. All right, I promise it'll be very quick, but hopefully very illustrative. Right now, I'm going to draw a larger curve, just to show. Okay, so I'm going to have a non-linear axis. Okay, let's say we have a normal distribution. So it's pretty normal. It's pretty symmetrical. No strong visibility of left skew or right skew. So it's a very nice distribution, even if there are minor areas where they differ from normal distribution. It's still very good approximation. But my scale, however, is going to be quite different. So this is 100, this is 1,000, yeah, and then you have 10,000, and then you have 100K, and 1 million, and 10 million. Yeah, you can see that even though this bell curve looks very nice and decent, the scale is very non-linear. So this is the log scale that we will talk about, but you understand, yeah? So now what happens? Suppose this is my x. Originally it was like that. If I apply log x, then what happens? I don't change the vertical spread because I'm not applying to the probability density of x. That means the y-axis. When I say log x, right, base 10, I am talking about applying the log base 10 function to these values of the x-axis. For example, 1000 occurs a lot. But after applying logarithm base 10, I get 3 because there are 3 zeros there, right? So now it's very easy to see. Just look at the number of zeros because it's base 10. So you can see that it is very easy without even using calculator. I can just write them down. And it is very linear. In fact, it's perfectly linear after the log because it's so artificially constructed by me, right? And what happens to the curve? No change. So it is still highest at 1000, the original value, and it is let me focus on making this as similar as possible. You see, it should not short circuit it. Okay, but you get the idea. So the shape doesn't change at all because all I'm doing is to alter the x-axis. Obviously, I cannot call this a log uh, chart, right? So this is the kind of log chart with uneven or rather exponentially scaled x values. But this one is a linear value, linear axis. And this is so because we apply the log on these values, not the y values. So we're not going to depress the curve or change it in any way. I need to say this curve is the same as this curve, right? Even though my drawing is not as perfect here. So this is entirely equal. Okay, so the curves are basically the same. There's no depression of the y values, the PDFs, right? The heights are still the same. And all we are doing is to change the scale. Whether we say change or whether we say compress, you like to see it as a motion, you like to see it as tear out the labels and relabel them, right? Up to you, whichever way that allows you to accept this change, right? So then you can understand why this kind of transformation is going to happen and it's going to be desirable, right? So we started off with a normal distribution on a non-linear x-axis. If we had straightened this to a linear scale, that means x originally was very, very right skewed, correct? Because 10 million is going to go off screen very far away, and 1000 is 10 times larger than 100, which is 10 times larger than 10. So it's going to stretch this curve to such a widely spread out basis that even at 10 million, there is still some probability density there. So it's very right skewed, very non-normal. And how do we make it normal? How do we make it more normal? It was normal, right? If you apply the log. So we apply the log base 10, and by our own construction, we started off with a perfectly normal distribution, right? So now we get these scales, which is basically linearized. Now, if you look at this log base 10 of x and you call it w, then w as a random variable, if you don't look inside and its relationship with x, is just any other normal distribution that we've been talking about. See, that's exactly the kind of notion that we are talking about. And we just need to apply the suitable log here. I use log base 10 to make the illustration of these numbers a lot more obvious so that you don't have to pick up calculator and start checking whether it's true or not. Yeah, but essentially it works for any basis. Okay. Now that we understand better this change, so let me just annotate it a little bit, right? So log x squeezes large right values to the left. So that's the effect. Okay, so this is normal. But scale is non-linear. Okay, So we apply log x, and then we get a very nice normal because the y values don't change. Okay, next, let's move on to the power index. Okay, and exponential models. Of course, I need another curve. So the first of all, let's just look at one example of nonlinearity. Okay, this is x, and the PDF, right? So and y, not the PDF. So x and y. So we start collecting dots, and suppose the dots are such that they show this kind of relationship. Yeah. So it's kind of curved. For example, x to the power of 3 generally will be like, I'm not going to draw because it's going to mess up my curve. So it's something like this, and then there's a sort of a inflection point, and then it curves downwards, right? So it can be like that, or it can be uh, logarithmic. It can be um, inverted parabola. So parabola normally is like this. It can be a sort of 1 minus x squared, and it becomes like this. So whatever is the case, we have this curve. Now, if you try to do the usual linear regression to give a line, you're going to have a lot of gaps. Remember the vertical gaps, they are errors. And so it will affect your R square, right? The quality and the reliability of your regression model. So one way out is to try, right? Try to transform it into a model that is more linear. All right, so this is perfectly linear. That would be nice. So we try to apply a function, and you guessed it, the logarithmic function, right? So that the bigger values get uh, a bigger penalty, get reduced more. And we need that, right? Because if you have very large value of x on the x-axis, you need to push it back in to reach this green line. It may be a more slanted green line, it may be a more slopey green line, doesn't matter, but that's the idea, right? So once you have this green line, then we can talk about what is this green line, and then find a way to make it work. So how do we find this green line is what we are trying to do. One, let's write down the model. The model is y equals to b0 x to the power of b1. So x changes, but b1 is constant. Right? If we apply logarithm, we cannot just pick x because there's no reason to. There's no science, there's no justification, there's no I mean, you have to, your x has to be very special just for you to say, let's just apply logarithm, change the x to log x. That is not the way we do transformation, right? So now that we have a proposed model, we know that y and x behave in such a way to give this curve. Yeah. So when we perform logarithm, we have to respect this nonlinear relationship. And what we're going to do is apply ln on both sides. Ln is basically log base e, yeah, on both sides. So when we do this, this is entirely legitimate. Doesn't matter whether your y and x, they are business variables, they are scientific measurements, they are social experiment measurements and data. Doesn't matter because this is a strict mathematical relationship. But then something happens, because when we do it this way, we can apply the properties of logarithm, that when you multiply two values together, you can split them apart and use a plus sign to link them back. Right? And I'm going to put another step here, which is that when you have x raised to the power of b1 and you take the logarithm, it is the same as b1 times logarithm of x. So we can just multiply by B1. So this is fantastic. Why? Because if you treat this as V and you treat ln of x as W, then we essentially have the linear regression of V and W. Because when you throw the values of ln y and ln x into the regression, so instead of doing regression on y and x, which will be not reliable because it's actually curved, right? That you process the values of y and x. In Excel, for example, there is a column of y, there's a column of x. You create two more columns. One is ln y, one is ln x, which are basically labels for v and w, right? Now you regress these two columns. So in R, instead of using ln y tilde x, like go refer to R if you're not familiar, you produce ln of y and ln of x, and then you ln v tilde w. You say v equals to ln y, w equals to ln x. So you now say ln v tilde w, and R will churn out everything, treating v and w as linear, and produce values C0 and C1. So from report, right? So from report, from R's reports, you get C0 and C1. Oops. Right, the y-intercept and the gradient for v and w, not the gradient for y and x. There's no meaning for y and x, right? Because the gradient changes all the time. So the constant gradient, B1, is obtained from C1. Now, because C0 is ln of B0, so to get back B0, we just take e to the power of C0. And our C1 reading off from R's report, or for that matter, Excel's analysis outcome table, Python summary report, you will get C0 and C1. But because in our analysis, C1, the gradient for the V and W, is also the B1 that we want for our original model. So we get B1 equals to C1. So that's it. Finished, right? So because the moment we have obtained the actual numerical values for B0 and B1, then we are done. Very, very easily. So that's applying the logarithm onto the model itself, right? So now we have this. Similarly, and now that you have seen one example, for the exponential case, it is very similar just as well. Exponential case is explosive upwards, like this. So your data points is going to be like this. So increase x by 1 unit, suddenly the y jumps up by twofold, fivefold, tenfold, right? So it jumps up. So the behavior between y and x is like this. And there are many cases, right, of applications. This could be the COVID-19 viral infection people, right? Number of people reporting sick. And if this shows COVID-19's death rate, well, that would be terrible. It's no longer a pandemic, right? It's a disaster, right? So it's like more and more people die every day. So very, very scary. And it could also be compounding interest, right? So that's also some sort of a raise to the power of, but not exponential. Compounding interest will be more like to the power of n. Okay, yeah, if time is the x-axis here, then as time passes, your constant is raised to the power of time. Then time increases, it will be exponential. So compound interest can build your retirement as it is due to this exponential effect. And yeah, many cases we have, for example, the spread of rumors, right? 1 to 2 people, 2 to 4 people, 4 to 16 people, and keep spreading, right? Spreading of rumor is like wildfire, and that's because it's spreading, reaching exponentially. Right? And of course, there are also many applications for these. Yeah, and sometimes, most likely, B1 is a small number. For example, it may be non-linear because it is square root. So b1 is not 1, because if b1 is 1 or near to 1, 1.005, right, then it's just linear. But if b1 is 0.5, 0.49, then basically we are implying, or we are saying that y is related to x in a square root relationship, and that's not impossible to find. And maybe b1 is near to 2. That just means y is x squared. So for example, y can be the property's area based on the length. The longer it is, I just measure one side, yeah? And I don't have time, or I'm not allowed to walk the other side of the property. However, I know from statistics that b1 is about 2.15. So if I know one side of the property, I can x raised to the power of 2.15 to estimate the total property area, right? So this area relationship around 2. Of course, if it's around 3, it is cubic, right? I can measure one side of a box and I can estimate the volume. And that is basically the idea, okay? Yeah, so let's look at this one. And what do we want to do? We want to do something similar. Okay, what we want to do is this time round to push down the y values. Okay, push down the y values, and or if that is not enough, because after applying the y values, we only reached here. So just taming the y is not enough, and we have to also tame the x value. So it could be that we also need to apply the x values so as to reach here. So this might come to here, right? So it may be distorted in a way because we may need to also apply some sort of a horizontal force. I hesitate to draw the arrows in because it will be looking very messy and confusing. But the idea is to bring down the y values a lot, right? How do we do it? Well, the original model was y equals to b0 e to the power of b1 x. Of course, if b1 is 1, then it's just e to the power of x. So we want to know what is the value of b1, right? So there's no a priori knowledge that b1 has b1 or something else, okay? So what do we do? And again, you can now imagine, we cannot just say, oh, we want to tame the y values. So ln of y equals to b0 e to the b1 x. Number one, maybe that works. But number two, it is still nonlinear. We don't get a green line, right? This line will have to be making sure that x is not on top but on the ground. Yeah. So that's why we need to again apply ln uniformly across both sides. And again, exploiting the properties of logarithmic operators, we can split these two apart. Ln b0 plus ln of e to the power of b1x. But ln of e to the power of something is the something itself. It is the inverse of exponential, or ln is the anti-exponential. Right, so ln of e to the power of b1x is just b1x. Finish. So we have just brought down the index to the ground. Excellent. So now, again, using our X-ray vision, we see that, right? Or we can just pretend that left-hand side is V, right-hand side, let's just call it W, even though you are definitely sharp enough to see this is just X, right? So we just regress V with X. So in R, you say ln V tilde X. That's fine, but just to be symmetrical in this discussion, we assign W as the a copy of X. And then from R's reports, I'm saying R, but you can use Python, you can use Excel, right? We get the y-intercept C0, which is this guy, right? And C1, which is the gradient for W, which is B1. But here is our derivation. We don't want C0 C0, C1. We want B0, B1 so that we can plug it in and realize our original model. So we have C0 is ln of B0, end up the same treatment. And our C1 is just B1. Right? Okay. And so what we want is C1 is just B1. So end up the treatment is pretty much the same. And that's good because we don't have a lot of work to do. Once we read out the C0 and C1 from the reports, we just do the intercept, raise it, by e to the power of, then we are done. So with this means with the knowledge, right, of B0 and B1, the values themselves, we already have identified this. Okay. So the original non-linear model, and then our job is done. Rather straightforwardly, isn't it? Okay. For the time left, I like to discuss about the interpretation of coefficients. Okay, so we begin by looking at at the border. I'm trying to see if there's enough space. Maybe we can squeeze in, maybe not. I'll try. Okay. Let's indicate this as interpretation of the coefficients. For the power index model, power index just means x is sitting on the ground. Exponential means x is sitting on the second floor. So for interpretation, we want to change x a little bit. Change x a little bit. Now, typically we say for every unit increase in x. So first of all, y is equal to b0, x to the power of b1. If we put x plus 1 to the power of b1, not impossible, but it's very nasty, very tough mathematics that we tend to get to nowhere. So what we do is we say that the new y prime is going to be when x is raised by 1%. So 1% is going to be 1.01 times x. That's true. Raised to the power of b1. Okay, and we note that this is essentially b0. Split them apart, both raised to the power of b1. So x raised to the power of b1 times 1.01 raised to the power of b1. You can see that? Or revise your high school exponentiation operations. So when we exponentiate to b1, we can split them, right? So 1.01 to its own b1, x1 to its own b1. Now what's the purpose? The purpose is that then we can perform a ratio. So y prime divided by y, right, is this right-hand side divided by this right-hand side. But this guy here is y, right? So straight away, we get 1.01 raised to the power of b1. And this is essentially 1 plus 0.01 raised to the power of b1. And this expression has, let me just highlight this. Okay, this 1 plus 0.01 raised to the power of b1 has an interesting form, because this form allows us to perform the Taylor series expansion. So we can do 1 plus 0.01 of b1, and then plus a bunch of expansions, basically 0.01 square, which means 0.0001. Right? So very small. Over 2 factorial, b1 times b1 minus 1 plus 0.01 cube, which means 0.000001. Many zeros. and b1 times b1 minus 1 times b1 minus 2 and plus infinitely many terms which we don't care, because from here, this bracket onwards, these will be 0.01% of the original value, which means very, very tiny, and this is even tinier and even tinier, and it's so small that we don't have to worry that much if we drop them in practice. So it's not going to affect too much. So in short, we can then say actually every 1% increase in x will lead to, right? It will lead to let me put approximately 1 plus 0.01 b1. So which means that this is percent, right? This is percent. So if we tag a percent, if we copy out the value and tag a percent means that when we put inside an equation, we divide by 100. For example, 7%, we don't write 1 plus 7%, we write 1 plus 7 divided by 100, so 1 plus 0.07. So this 0.01 is like throwing it away and put a percent. Okay, so if we can understand that, then it implies that for each percent increase in x, because we had increased x by 1%, all right, leads to b1. Just copy the value b1, copy the value. If it's 5, then copy 5, right? 7, then copy 7. So leads to b1%. Okay, let's just highlight this. b1% increase in y. Of course, if b1 is negative, then that means every percent increase in x will lead to, for example, minus 2, and negative 2% increase, which means a decrease of 2% in y. Okay, quick example. What's my example? Y, for example, is equal to 3, that means b0 is 3, times x to the power of 0.07. Okay, so b1 is 0.07. So b1 is 0.07. Then now what? So example, x equals to 2. X equals to 2 leads us to get 3 times 2 to the power of 0.07. So that's y equals to 3.1414915 and 00509. Okay. And we need to increase this by 1%. So after using calculator, we get y prime, right? This is y prime because we have increased x by 1%. 3.1513442709. I need this to be more precise so that I can capture, the so-called actual increase. Okay, so what happens? Y prime over y. If you divide, you get 1.0006967,658. Okay, so that is approximately, if you take away the 1 and you multiply by 100 to get a percent, 0.069, right? So 0.069% increase in the y. That's roughly indicated by b1, right? b1 is 0.0. 7. So that's like 0.07% increase in y. So that's nice. That's nice. Okay. But this has to be done only when b1 is small enough. Okay, so not really true when b1 is too large. So this is true. This approximation is true when b1 is, let's say, small. How small is small? Let's put it as less than 10, roughly speaking. Then the approximation is okay, right? But when b1 increases, then we'll have more and more deviation. Then b1 does not imply the percentage change in y anymore. But we'll see an example later. But let's finish up with the other important discussion, which is to talk about the interpretation of coefficients in the case of exponential model. So how does this go? Again, interpretation, right? So we want normally we say x increases by 1 unit. What happens to y? Yeah. So in fact, here is nice, and we can do that because when we have y prime is equal to b0 e to the power of b1, and we increase x by 1 unit, like that, we can split, right? We can split the exponential into b0 e to the power of b1 x, and also because of the plus b1 that's multiplied in, we can multiply by e to the power of b1. Yeah, because b1 is multiplied into x, then b1 is multiplied into 1, and we can split because the plus in the index is multiplying by the exponential of the index. Okay, so what does this do for us? Essentially, you can see this is already similarly, this is our y already, isn't it? Because it's the same format here. So we can divide through, and we realize this ratio is simply e to the power of b1. That will be the exact form. So every unit increase in in x is e to the power of b1 minus 1, right? And then you have to times 100, right? Percent increase in y. But that's a mouthful. So theoretically, we want to say theoretically, yeah. So that's just theoretically. Let's just say. So this implies that for 1 unit increase in x leads to divide by 100, right? So 1 over 100 e to the power of b1 minus 1%. This 1 over 100 and percent cancel out basically, right? Increase in y. Sorry, I shouldn't be writing 1 over 100. It should be 100 so that the 100 and the percent cancel out. Okay, sorry. Okay, so we have this theoretically, right? So theoretically. But this is such a mouthful that it doesn't really help in terms of quickly understanding the impact, right? So we want something that is helpful, not just accurate, but we want it to be easily giving us a feel of what is this large, is this small, is this affecting us in a good way or bad way, right? So that's why we want to push it a little bit more. How to push it is going to be what we are going to try here. So if b1 is less than 1, then we have y prime over y is equal to 1 plus b1 plus b1 square over 2 factorial. That's right, the Taylor series expansion for exponential function, plus b1 cube over 3 factorial plus dot 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 dot, right? Similar kind of mathematical analysis. So again, we're going to say if b1 is small, less than 1, b1 square is smaller, then you divide by 2 factorial. Then b1 cube is yet even smaller, and you divide by 6 because it's 3 factorial. And you divide by a bigger and bigger factorial. And you raise to a smaller and smaller, bigger and bigger power, which makes the whole term smaller and smaller, right? So all these terms are going to shrink to something that we don't care about. Therefore, we can conclude that this is approximately 1 plus b1. Okay, so that means for 1 unit increase in x, right, it will lead to again, using the same style, 100 times this b1, then put a percent. 100 times b1, then put a percent increase. So it's percentage increase, right? The bigger the x, right? The larger the increase in the y. Okay, increase in y. Okay, so that is what our takeaway is. Now it's important to note that this is true. This approximation is true only for the case of b1 less than 1 here. Okay, so very important to note. If b1 is 1.5, right, this term will start exploding. b1 1.5 square is going to be bigger than 1.5. 1.5 cube is going to be way bigger than 1.5, and so on, right? So bigger than 1, these will start to increase, and the terms will have to be added in. It's no longer ignorable, right? So we have to use back this more accurate formula. Okay. And I just want to highlight the conditions that we applied. Okay, so let's again run a quick example. Example: y is equal to 3, so b0 is 3, times e to the power of 0.07x. So this means that b1 is 0.07. Okay, so first of all, b1 is less than 1, way less than 1. The smaller the better, so that our approximation is more accurate, but never exact, or never exact. So when x equals to 2, we get y is equal to, you do the math and calculation, I got 3.450821 3966. Okay, you can check your math, right? So x equals to 3 because we increase x by 1 unit, and we want to check y prime is going to be equal to 3.701341799. Okay, now let's divide, right? So y prime over y is going to be 1.07. You can also divide and check 25081813. Okay, so our so here what happens? So the increase is approximately 7.25%. Okay, what is our prediction? Our prediction, our b1 is 0.07 times 100 is 7%. 7%. Actual increase 7.25%. So already not very close. Although if so we are going to read and treat it as 7% increase in y, when actually it is a bit more. A bit more because we have dropped the positive terms. These are the little bit infinite terms that add up to 0.25 here, right? So the smaller the better, right? So if b is very, very small, then you'll be right. If b is near to 1 but smaller than 1, like 0.94, this term is the actual increase is going to be way larger than 0.94, right? So multiply by 100, 94%, way larger than that. So the the term will be less and less stable and less accurate. Okay. So basically, that's the interpretation part. For the correct interpretation, just final note here. Sorry, I have a bit of space, so we can add this final counter example. Right? What happens if your B1 is large? Right? So for the power index model, so for y equals to B0, x to the power of B1, right? Bad examples. So let's say y is equal to bad example, I want to use purple. Okay, so y is equal to 3 times x to the power of 18.7. So that means B1 is 18.7. Yeah, okay. Okay, so 18.7 did not follow the condition. And what happens? So we proceed to evaluate at the point of x equals to 2, and this gives y equals to 1277562.553. Okay. So again, we have to increase by 1%, so we get x equals to 2.02. This gives y equals to a rather larger number, 1538834.319. And if you proceed to divide to find the increase, percentage increase in y, you get 1.2045. So minusing 1, which means that that's an increase of 20.45%, right? But what did B1 say? B1 says you should have 18.7% increase. Yeah, so this number and this number no longer look even alike anymore. It's like 10% error or more, right? Yeah, so bad example, really bad, right? Okay, next, quick bad example for y equals to b0, e to the power of b1x. Bad example. Okay. Well, you just need to disobey this condition, b1 less than 1 will do. So for example, with a data set, we obtain the regression coefficients, y equals to, what is it? 3 times e to the power of 2.34 x. Okay, so this implies that b1 is 2.34. So is 2.34 following the condition? No, it's more than 1. Okay, so what happens? Well, we want to interpret. According to our interpretation, for 1 unit increase in x, it will lead to 100, right? So 234% increase in y. 234%. That's fine, it's more than 100, but is 234 even correct? So let's try. At x equals to 2, we get, substitute in, we get y equals to 323, sorry, not 3.23, 323.3102, 1772 yeah. And because we need to increase x by 1 unit, we evaluate at x equals to 3, and at this point we get 3356. Notice it's 3356, 3356. This is 323. Right, 359. I think the rest of the decimal places are not going to be very useful anymore, but let's just chaff them in. Okay, now we divide, we get y prime over y is equal to, just divide these two numbers, and what happens? Easily 10 times, right? So 10.38123656. Okay, what happens? According to our prediction, it should be this times 100, so 234%. This is how much? This is minusing 1, right? We get, so it's 1 plus 9.38. Right, so that means it's 938%. That's way wrong, right? So 234% to 938%. Way wrong. So our B1 is totally powerless to help predict or understand what it means by per unit increase in X leads to 234% increase in Y when actually it's 938% increase in Y. So the only way to get this done is to use the correct formula, 100 times e to the power of B1 minus 1% increase in Y. Okay. All right, that's all I have to discuss for nonlinear regression today. Thank you very much for your attention, and see you in the next video. Bye.